Welcome to Chem with Chem. In this session, we're working Chemistry Paper 2 from the May-June 2024 sitting. Let's get right into it. Sodium thiosulfate solution reacts with dilute hydrochloric acid to produce sodium chloride solution, sulfur dioxide gas, solid sulfur, and water. To investigate the effect of temperature on the rate of reaction, Paul performed different experiments using sodium thiosulfate and dilute hydrochloric acid. For each experiment, the same volume and concentration of sodium thiosulfate and dilute hydrochloric acid were reacted, but at different temperatures. The temperature was measured at the start of each experiment, and the thermometer readings for experiments 3 to 7 are shown in Figure 1. First thing we're asked to do here, Part A, define the term rate of reaction. Now, rate of reaction is the change in the concentration of a reactant or product per unit time. So let's get that down. That will give us our 1 mark. Now, we'll need to know the readings or read off these temperature readings for part C1, which we'll put in a table in a little while. So let's just make a note of them from now, and then we'll fill them out a little later on. So the first thing we do when we're reading off values for any instrument is to figure out what each marking represents. So in this case, we're seeing that each marking, we're going up by 0.2 degrees Celsius. So the first one there, the first reading here would be 14 degrees Celsius. And then this one is at 20, 20.2, 20.4. This is 20.6. And that looks like halfway between 20.4 and 20.6. So we'll call it 20.5. And then we have this is 27. And then this is 33. And then the last one here is between 35.4 and 35.6. So we'll call that 35.5. All right, so we're going to hold on to those values. We're going to need them in a little while. So part 1 of 1B, write a balanced chemical equation for the reaction between sodium thiosulfate and the dilute hydrochloric acid. So they gave us the formula for sodium thiosulfate. That will be an aqueous medium reacting with hydrochloric acid. That's HCl. That's also aqueous. Now that will give us salt. Sodium chloride is the salt. We will get solid sulfur. We'll get sulfur dioxide gas, and we'll get water. Of course, we'll have to balance. Well, we have 2 sodium on the left-hand side. We should be seeing that, 2 sodium over the left-hand side. So to fix that or to balance that, we put a 2 in front of the sodium on the right-hand side. Putting a 2 in front of the sodium on the right-hand side causes the chlorides on the right side to be 2. So we need a 2 in front of HCl to balance that. And once we do that, everything else should check. We have S2 on the left, and we have 1 sulfur here from sulfur the solid, 1 sulfur from sulfur dioxide. So that should fix it. Now, part 2 says, describe a test and state the observation that can be used to confirm the presence of the sulfur dioxide gas produced from the reaction. So what we'll do in this case, we'll bubble the gas in acidified potassium dichromate 6 solution, and we note our color change. So when we do that, we should get our orange solution changing to green because our sulfur dioxide is a reducing agent, and the acidified potassium dichromate 6 solution is a very powerful known oxidizing agent. So we'll bubble the gas. Right, so we could also use acidified potassium manganate 7 solution, which is purple, and upon bubbling the gas through it, we would get it changing from purple to colorless. Determine the mass of sulfur dioxide produced when 50 cm cube of the gas was collected at STP. All right, and we're told here that the molar volume at STP is 22,400 centimeters cubed. So what we need to do in the first part of this question, we need to find out the number of moles represented by this 50 cm cube. So we'll just convert the 50 cm cube that's given, we'll convert that to moles, and then we want mass after, so we'll convert from mass to moles after. So first part, we're going to take the 50 cm cube and we're going to convert it to moles. So we'll say we're pretty much just dividing by 22,400 cm cube per mole, and that will give us 0.002 moles of the gas. Now we want the mass of, we want that number of moles in terms of mass of SO2. So we'll have to take SO2, and they gave us the RAM. So we'll take the number of moles that's given and we'll multiply by the molar mass. All right, so the molar mass here would be SO2. That's 32 from sulfur, and then 16 times 2 for oxygens, 2 oxygens. So that would give us 32 plus 32, which is 64 grams per mole. So that's 0.002 moles times 64 grams per mole. And that will give us 0.143 grams of sulfur dioxide. So we're at part 1 of C. We read off our temperature readings earlier, so we're just going to put those in. We had made a note of those, so let's just put those in for minute 3, 4, 5, 6, and 7. So we have 14 degrees Celsius, 20.5, we have 27, we have 33, and we have 35.5. Now what we're supposed to do for part 2, we're supposed to calculate to 3 decimal places the rate of reaction for each experiment, given that the rate is 1 over time, and we're to record our results in column 4 of the table. That's over here. All right, so 2 were done for us. So we're just going to take the time, whatever is given, and we're going to find the inverse of that. So we're going to take 40. I'm going to say 1 divided by 40, and that will give us 0.025. 1 divided by 24, which is 0.042. Then 1 divided by 15, which is 0.067. Then we have 1 divided by 11, 0.091. And 1 divided by 10, they want it to 3 decimal places, so that will be 0.100. We'll get 5 marks for doing that. Now, in the next part, for part 1 of D, we're supposed to use the axes provided in figure 2 on page 7 and plot a graph of rate of reaction versus temperature for experiments 1 to 7. We're to draw a smooth curve through the points, and all of that will give us 5 marks. This is figure 2, graph of the rate of reaction versus temperature. So let us plot our points. Before we plot, we need to figure out what the scale is on each axis. Let us look carefully. On the x-axis, we have 2 centimeters. On the x-axis, 2 centimeters are representing 5 units. That's 5 degrees Celsius. On the y-axis, we have 2 cm being used to represent 0.01 per second. All right, so let us sharpen our pencils and plot to the best of our ability. Let's plot our points. We're going to use small x's or encircled dots. I'll use encircled dots for the plot. So let us go for the first one. We have at 5 degrees. 5 degrees. Temperature is on the x-axis, so we'll find 5 degrees. So at 5 degrees, now we shouldn't really mark it there. Just put a dot there for us to realize that's where we're going to be plotting on our x. So at 5 degrees, we're going to find 0.017. 0.017 should be here. So we'll circle that. And then at 10 degrees Celsius, we have 0.02. So we'll find 10 on the x and we'll go to 0.02. We put an encircled dot there, or we can put small x's. Then at 14 degrees Celsius, we have 0.025. At 14 is here. We have 0.025, so we go around to 0.025. At 14, 0.025 is here. Then at 20.5, we have 0.042. At 20.5, 20.5 is here. We're gonna go up, we have 0.042 at 20.5. We put our encircled dot, and then at 27, we have 0.067 at 27 degrees, 0.067. At 27, we have 0.067. All right, so 27 is here. Let's find 0.067. This is 0.065 up top, so we go 0.6, 0.7. We put our encircled dot. Then at 33, we have 0.091. At 33, 0.091. 33 is here. Encircle dot is there. And then the final one at 35.5, we're at 0.1. 35.5, we're at 0.1. So that will take us 35.5, we're at 0.1. Let's fix that. That's our encircled dot. And then we're supposed to draw a smooth curve through the points. So we don't use a ruler, we do this free-handedly. That will be that. Our curve should be smooth, and that is it. Let's see what we're asked next. So from this, we're going to answer, then we write it on. Part 2 of D says, using the graph you plotted on page 7, so we're on page 7, explain how the change in temperature affects the rate of the reaction between sodium thiosulfate and hydrochloric acid. If we look, we're seeing that if we look at it carefully, we're seeing that temperature is increasing as we go over to the right. But we're noticing that as temperature increases, so is the rate of reaction increasing. All right, so all we need to do for that part in the next section, as the temperature increases, so as the temperature increases, the rate of reaction between sodium thiosulfate and hydrochloric acid increases. Question 2. The most stable form of the element oxygen has a mass number of 16 and an atomic number of 8. It can also exist as a radioactive isotope. Define the following terms. Part 1, atomic number. It's the number of protons in the nucleus of an atom of an element, and for mass number, it's the sum of the protons and neutrons. And then we're being asked in part 3 to define isotopes. So isotopes are atoms of the same element. By same element, we mean they have the same number of protons. So atoms of the same element with different number of neutrons. So if the number of neutrons is different, the mass number would be different. So we could say hence different mass number. So there we have it, or 3 definitions. That's 4 marks. Part B of 2, use a dot and cross diagram to show the bonding present in oxygen gas. So we're talking about a molecule of oxygen. So oxygen is in group 6. So there are 6 valence electrons. So what we're going to do, we're just going to write the symbol O. And we're going to show how those 6 valence electrons are surrounded, in a dot and cross diagram, just to give you, just to illustrate the bonding taking place. So, so each of them will share 2 electrons in what we call a double bond. So we'll just put oxygen as the symbol, 2 atoms of oxygen. So these electrons are not involved in bonding, but these in the middle are involved in bonding. That's one way to show it. Or we could actually overlap them, the valence shell, and would put the non-bonding electrons here from 1. These will share. Put 1, 2. So there we have it. O2. Either of these 2 arrangement will give us the marks. There are many uses of radioactive isotopes in everyday life. List any 3 uses of radioactive isotopes. So I guess the easiest one would be carbon dating, where we can tell the age of fossils or how long ago they were alive. So we use carbon-14 for that. We can use radioactive isotopes as tracers in medicines. For example, iodine-131 is used to tell if there are defects in the thyroid gland, because the thyroid gland absorbs iodine and makes thyroxine from it. So if it's suspected that the thyroid gland is defective, a small amount of iodine-131 is ingested, and then later on it's checked. The body is scanned to see where it is. If it's found in the thyroid gland, then the thyroid gland is working. If it's found in the kidney, then it means that if it's found in the kidneys, then it means that it's not, the thyroid gland is not absorbing iodine as it should. So we use it as tracers in medicine. So that's iodine-131. We use them to kill cancer cells, and we'll be specific here, to kill cancer cells. And here we're talking about cobalt-60, and we'll use that to kill cancer cells. I'll just leave that right here. There are other uses. We use them to generate power in nuclear plants, right? So power generation. in nuclear plants. So that's uranium-235. And they can be used like plutonium-238 can be used as an energy source in pacemakers for the heart. But they asked for 3, we gave them 4, mentioned 5. That should give us our full marks. Top it off, the last 5 marks. Part D, carbon burns completely in excess oxygen to produce carbon dioxide. They want us to write a balanced chemical equation, including state symbols, to show the reaction. So carbon is a solid. It burns in oxygen. Oxygen is diatomic. So we write that as O2, elemental oxygen, O2, and we get carbon dioxide. So we write CO2 gas. And that's just balance. 1 carbon on the left, 1 on the right, 2 oxygen on the left, 2 on the right. Then they say in part E, carbon burns in limited oxygen supply to produce carbon monoxide. Write a balanced chemical equation, including state symbols to show this reaction. So we're going to start. Carbon is a solid. We're still writing oxygen gas as O2. Then we write, instead of carbon dioxide, we write carbon monoxide. That's also a gas. So we now need to balance. We have 2 oxygen on the left, but 1 on the right. So we put a 2 in front of the CO, and that also changes the carbon to 2. So we put 2 in front of the carbon on the left to ensure that it's balanced. And just like that, you have 15 marks for number 2. On to number 3, it's an organic chemistry question. Compounds A and B are straight chain hydrocarbons whose molecular formulae are C5H12 and C6H14 respectively. State 1 natural source of hydrocarbons. All right, so we could give petroleum or crude oil, or we could say natural gas. State 2 uses of compound B. So compound B is the one with the formula C6H14. C6H14, so it means we're talking about an alkane with 6 carbons, so that is hexane. So well, hexane can be used as a fuel. It can also be used as a solvent. Non-polar solvent, so it can dissolve non-polar substances. They want us to draw the fully displayed structure of compound A. Compound A is C5H12, CnH2n plus 2, so that's pentane. So we're going to draw our structure with 5 carbons long. And of course, we're going to put on our hydrogens. So this is a saturated hydrocarbon. 6 carbons, 12 hydrogen. That's it for that page. We'll move on to the next page. Draw the fully displayed structure of compound B. Compound B, we said, as the formula C6H14. So we're drawing a skeleton or backbone formed from 6 carbons. And we'll get 2 marks for doing this. Okay, part C, part 1 of C. List any 4 general characteristics of a homologous series. All right, so the first one, members of homologous series have the same general formula. Members have the same functional group. Members of the same homologous series have the same functional group. Consecutive members of the series differ by a CH2 group. Fourthly, members all possess similar chemical properties. Part 2, deduce the homologous series to which compounds A and B belong. So we mentioned pentane earlier. So A, we said was pentane. B, we said is hexane. So those are all members of the alkane series. So they belong to a homologous series called alkanes. Oh, for the last 3 marks to make 15 for number 3, part D. Compound B, C6H14 burns completely in oxygen to produce carbon dioxide and water. Write a balanced chemical equation, including state symbols for this reaction. All right, so that's C6H14. That would be a liquid. Plus oxygen will give us CO2, gas, and water vapor. H2O, which would be a gas since that's combustion. All right, so first things first. So we have 6 carbons on the left. So we would put 6 in front of the carbons and the carbon dioxide on the right. Now when we do that, that balances the carbon. We now move on to the hydrogen. We have 14 from C6H14. We have 14, so we'll put a 7 in front of the water. And we get 7 2 is 14 over on the right-hand side. So that balances the hydrogen. So we now would move on to the oxygen. On the right side, we have 6 2 is 12 from the carbon dioxide. That's 12 oxygen there, plus 7 here from the water. 12 plus 7 is equal to 19. So what we would do over on the left-hand side for oxygen, it's diatomic. So we would put 9.5. But we cannot have half a molecule of oxygen. So instead of putting 9.5 in front of the oxygen, we double that number. Since we cannot have half of an oxygen molecule. We cannot have that. So instead of putting 9.5, we double that 9.5 and we'd end up with 19. Now, if we double the 9.5 for the oxygen, we have to double the hexane. So we put a 2 here. Everything would be doubled. So the 6 that was in front of the carbon dioxide, we'd have to now change that. We'd have to now change that to 12. We'd have to change that to 12. The 7 that was in front of the water would have to be changed to 14. So we'd have to fix that. So the final thing would be this. 2 hexane plus 19 oxygen to give 12 carbon dioxide and 14 water. Number 4, magnesium and lead are metals often found in living things in the environment. Part 1 of A, explain metallic bonding in metals. Notice they did not say between metals, they say in metals. So all we need to state here is that it's metallic. This is kind of redundant because if it's a cation, it's coming from a metal. So it's metallic cations held together, or we can say embedded, lodged in a sea of mobile, or you could say delocalized electrons. Give the reason why metals conduct electricity in the solid form. So to kind of give the reason here, we need to have an appreciation of what the structure would look like. So let's say these are cations. So these are cations. This is representing a metal. So that would be a cation. And then here would be your electrons. So the cations would be held together by this sea, or they would be embedded in a sea of mobile electrons. These electrons can move. If we were to apply a voltage to this piece of metal, then the free electrons would move and would carry the current. So that's exactly what we need to state right here. The free electrons in the sea of mobile electrons can move and carry a current if a voltage is applied. State any 2 harmful effects of lead and its compound on living things and their environment. Lead can cause damage to body tissues and organs. And one of the reasons they've taken it out of pencils, exposure to lead can cause damage to the brain, damage to the central nervous system, can result in you or that child going into a coma. It can even cause death. So it reduces IQ as well. It definitely messes up the central nervous system. So it can result in mental retardation. So that's why it's important that lead is not in the paint for toys for children, and lead is no longer used in pencils. Part B of 4, a chemistry student conducted a series of experiments using an electrolytic cell to test the conductivity of magnesium chloride. The materials used to set up the apparatus and the students' observations were recorded in table 2 below. All right, so we're seeing in experiment 1, the electrodes used were PVC pipe. The electrolyte was dilute magnesium chloride. The bulb did not glow. The bulb did not glow. Then the observation that the electrode, no visible reaction. In experiment 2, the electrodes used was graphite. The electrolyte was dilute aqueous magnesium chloride. The bulb lit up and the gases were produced at the anode and at the cathode. Now, for 3, the electrodes used was platinum. They were platinum. The electrolyte was solid magnesium chloride. The bulb did not glow and there was no visible reaction. Then we're going to answer the questions based on these observations. Explain why the bulb did not light in experiments 1 and 3. All right, so let's look at experiment 1. In experiment 1, we had dilute aqueous magnesium chloride as the electrolyte, but the electrode was PVC. So we could say here that PVC or plastic PVC electrode is a covalent compound and would not conduct electricity. For experiment 3, if we look at experiment 3, metal electrode was used, platinum, good. But the electrolyte was solid magnesium chloride. So in solid magnesium chloride, all the ions present are involved in bonding. So it's an ionic compound, but all the ions that are present are involved in bonding. They are not set free, so they're involved in bonding in the ionic lattice and cannot move. They're not free to move and carry a current. That would give us our marks right there. So in part 2, we're to explain why the bulb lit in experiment 2. So let us look at experiment 2, where the electrode used being graphite, where dilute aqueous magnesium chloride as the electrolyte. So let's go over and write our answers. All right, so we're gonna say graphite as an electrode has mobile electrons that can carry current, and the ions in magnesium chloride in aqueous magnesium chloride are free to move in the aqueous state and carry a current. And then we're to state the process that took place in experiment 2. That's the one where the bulb lit. The name of the process is electrolysis. And magnesium in part C, magnesium readily reacts with air, well, with oxygen in the air. Write a balanced chemical equation for this reaction. All right, so let's just go Mg plus oxygen, oh my God, gives MgO, and of course O2, so we need 2 in front of the magnesium oxide and 2 in front of magnesium, and that would give us our full marks, 15 marks for question 4. For question 5, part A. Proteins and starch are examples of natural polymers which are formed through the process of condensation, polymerization. Part 1. Define the term polymer. So a polymer is a macromolecule made up of many repeating monomer units. It must be 50 or more. Define the term condensation, polymerization. So this refers to a polymer that is formed where monomer units join with the elimination of a water molecule. And since it's condensation polymer, condensation should tell us that water is being formed. The manufacturer of ethanol makes use of the fermentation process. Define the term fermentation, and this is for 3 marks. So fermentation is the process by which we could say carbohydrates, but we could say sugar as well, by which sugars, which is a carbohydrate, are broken down anaerobically with yeast to yield or produce ethanol. And they want a balanced chemical equation, including state symbols, to show the process of fermentation. So we'll start with what we know. C6H12O6, that's glucose, would be in aqueous medium. And we're using the enzyme known as zymase, that's in the yeast. This will give us ethanol, 2 of it in aqueous medium, plus 2 carbon dioxide. In part 3, draw the fully displayed structure of ethanol. All right, F means 2, so it's 2 carbon atoms. And the OH group could go on any of the carbon atom. All right, so we just need to put on the hydrogens here. So that's our C2H5OH. Didn't ask for that, but we mentioned it in the previous question. Next question. So here in part 4, they want us to, well, let's read what the question is saying. So the remaining 4 for the 15 marks here, full marks. During a demonstration of the winemaking process in the school's food laboratory, a technician separated a pure sample of ethanol. However, the flask was not labeled and water was accidentally poured into the sample. Using a line diagram, draw and label the apparatus that could be set up in the chemistry laboratory to obtain the pure ethanol from the contaminated sample. We wanted the setup here for fractional distillation. So let's see if we can do a simple line diagram. So this would be our round bottom flask. From this, we would have our fractionating column. Forgive me if my lines don't connect, since I'm on screen. Thermometer would be here. Right? So these would be our glass beads, providing a large surface area. And from here now, we would have a little exaggerated. We would have a connector here. And here we would have this going all the way to the collection flask. But we need our condenser. Water goes in from the cool end. H2O in, H2O out. And then we'd have our collecting flask. All right, just to label, this is our heat would be applied here. That's our light bead condenser. This is our fractionating column. That's our thermometer. And this is our collecting flask. And that would give us full marks. Number 6, Alka-Seltzer and Epsom salt are common remedies used in the Caribbean. Alka-Seltzer is an antacid used to treat upset stomach, and Epsom salt is used to treat sprains and muscle pain. The active ingredient in Alka-Seltzer is sodium bicarbonate, that's NaHCO3, and Epsom salt magnesium sulfate. Notice they did not give you the formula, they just told you magnesium sulfate. Water is called the universal solvent because it dissolves many substances. Epsom salt and Alka-Seltzer work by dissolving in water. Part 1. Explain why water is a good solvent. Well, we could always begin by saying water is a good solvent because it is polar. All right, so what makes it polar? What makes water polar? So this is water, H2O. So the oxygen is more electronegative, so it pulls more of the electron towards itself in the bond. Though the electrons are shared, because the oxygen is more electronegative, it's stronger at pulling electrons towards itself, creating a partial negative charge over that side of the molecule. The area from which the electrons are pulled develop a partial positive charge. So this results in the molecule being polar. That OH bond right there is polar. So let us put that in a sentence or two. All right, so as a result of all that was said just now, water can therefore interact with and dissolve ionic compounds and polar covalent compounds. All right, state two properties of water other than it being a good solvent. So we need to state it has a high specific heat capacity for its size, or for the size of its molecule. It has a relatively high boiling point. It has a relatively, we say relatively because we're comparing it to other molecules with similar molar mass. So it has a relatively high boiling point, relatively high melting point as well. It has a high heat of vaporization, and it also has a high surface tension, but they ask for 3. State any 2 other compounds besides Alka-Seltzer, that's sodium bicarbonate and magnesium chloride, Alka-Seltzer and Epsom salt, any 2 besides those that dissolve in water. So we could give sodium chloride and we could give glucose. All right, glucose is a covalent compound, but it is polar, so it dissolves in water. So they're very common. That's your sugar and your salt. All right, so we're looking at what's right in front of us in the hole. Continuous use of Epsom salt in water may cause hardness of water. This does not happen with Alka-Seltzer. Hardness of water here does not mean the water is literally hard. All it means is that a certain ion, hardness of water, comes about when we have Mg2 plus and Ca2 plus ions dissolve in the water. Aqueous magnesium ions, aqueous calcium ions. So whenever we have that in water, the type of water hardness caused by this, in the case of Epsom salt, would be permanent hardness. And it doesn't mean the water is tough, it just means that it has calcium ions and aqueous magnesium ions. Explain why Epsom salt causes hardness of water. So this is why. So MgSO4 is soluble in water. So it dissolves, releasing Mg2 plus, well, aqueous Mg2 plus ions, which is one of the ions responsible for permanent hardness. And here we're to part 3, explain why boiling the water will not remove the hardness caused by Epsom salt. For us to understand this, we have to appreciate what happens, or when is it that we can use boiling to remove the hardness of water. Now, if we had magnesium hydrogen carbonate or calcium hydrogen carbonate. So let's look at an example. If we actually had we had magnesium hydrogen carbonate, if that were the ions we had when we boil this, let's just put boiling right there, or heating. When we heat that, it would form magnesium carbonate, and we know that all carbonates are insoluble except sodium, ammonium, potassium. So would get magnesium carbonate precipitating out, right? Okay, and that would give us also water and CO2. So if that were the case, if we had this ion or calcium hydrogen carbonate, then we could heat and we would end up with the solid being formed. We'd end up with a precipitate of magnesium carbonate or calcium carbonate. We'd get that out as kettle fur. But in the case of Epsom salt, we have magnesium sulfate. So we have a different story here. Boiling will not result in any precipitation or any precipitating of the magnesium sulfate. It doesn't break down to give you anything that's insoluble, so we'd get rid of the ions. So what we need to bear in mind, again, is that over here, the ions are in the aqueous medium, but over here, they are in MgCO3 in the solid state. So anything that removes them would be reducing the hard. That removes the magnesium 2 plus ions would be reducing the hardness of the water. So to answer, explain why boiling the water will not remove the hardness caused by Epsom salt, we need to state that magnesium sulfate is stable and does not break down on heating, nor does it form a precipitate containing the Mg2 plus ions and heating. A little redundant, but we get it. We got it nonetheless. So the Mg2 plus ions will still persist. The Mg2 plus aqueous ions would still be present on heating, so the water remains hard. The next question, we kind of answered it indirectly by speaking about when we can actually reduce or remove the Ca2 plus or the Mg2 plus ions by boiling. So here they're asking us to identify two salts that can cause hardness of water and can be removed by boiling. So would have calcium hydrogen carbonate or magnesium hydrogen, and magnesium hydrogen carbonate. When used as an antacid, part 5, Alka-Seltzer neutralizes the hydrochloric acid in the stomach, and they gave the formula of HCl. Write a balanced chemical equation, including state symbols, to illustrate this process. So sodium bicarbonate, NaHCO3. If you put solid, it would be good, but then again, you would probably add this to water. So it would be in aqueous medium, this plus HCl, stomach acid. Now this is a hydrogen carbonate and an acid, so we would get a salt. Sodium chloride is our salt, that's aqueous. We would get water and we'd get carbon dioxide. All right, I'm seeing one sodium on the left, one on the right, one chlorine on the left, one on the right. The carbonate breaks down to give CO2 plus the oxygen from the water. So this looks balanced. So that would give us our full 15 marks and full marks for the entire paper. Now, how did you do? If you found value here, then be sure to share this with someone else. If you like what was done here, be sure to leave a like. All right, couple later.